This lesson is on differentiating log functions. Now you may remember from the graph of the log function that the graph of the log function went something like this, where the x-intercept was 1, and we also drew the gradient function on top of this graph, and it looked like a hyperbola. That's the worst hyperbola I've ever drawn, but that's why the derivative of log x equals 1 on x. Okay, and likewise you can extend that to if you have the log of f of x, then the derivative of log of f of x is f dash x over f of x. So let's apply these rules to differentiate some log functions. So in question 1, if we let y equal log of 3x, then y dash, or dy dx, equals the derivative of 3x, which is 3 over 3x, and that will simplify to 1 over x. So that's one way of writing the notation. In number 2, I'll just mix it up and use a different notation. We'll say d dx, the derivative of log of x squared plus 5. Okay, just be careful. I notice in some of your books the notation that you're using isn't quite correct, so making sure you put the proper notation down for saying what the original function is, and when you differentiate, put the correct notation in front of that. So differentiating log of x squared plus 5 will be the derivative of x squared plus 5, which is 2x, over x squared plus 5. So differentiating log functions, I think, is really actually quite easy. Okay, in number 3, we are differentiating the log of 1 minus 2x. So maybe we'll do different notation as well here. We'll let y equal log of 1 minus 2x, and then we want to find the derivative, which is dy dx, and it'll be the derivative of 1 minus 2x, which is negative 2, over 1 minus 2x. Oops. Okay, and that can't be simplified any further. Alright, differentiating log of x plus 3 times 2x minus 1. So you could do this two ways. You can either use the first log law to split these up and then differentiate them separately, or you can expand the brackets using FOIL. So x plus 3 times 2x minus 1. So we've got x times x is 2x squared. X times minus 1 is minus x. 3 times 2x is 6x, and 3 times minus 1 is minus 3. Collecting like terms, we'll have 2x squared. 6x minus x is 5x, minus 3, and then we'll differentiate this. So we will find the derivative of d dx of the log of 2x squared plus 5x plus 3. And we're differentiating log functions. It is the derivative of f of x. So the derivative of 2x squared plus 5x minus 3 is going to be 4x plus 5 over the original function, 2x squared plus 5x minus 3. This doesn't look like anything else can cancel there, but remember that denominator was originally in factorised form in the question. Either of these two answers would have been fine. I guess it helps if you factorise to see if you can cancel anything on the numerator, but we can't in this case. Alright, now question 5 and question 6, they look very similar, don't they? The only difference is that in number 6, we've got log of x was all in brackets raised to the power of 3. So they're very different, and we're going to get different answers. So in number 5, if we'll use this notation. I think this notation is pretty good. d dx of log of x cubed. So that means we are finding the derivative of x cubed, which is 3x squared, over x cubed. And we can cancel and simplify there. So that will simplify to 3 over x, because we can cancel x squared there and x squared there. Whereas in number 6, this is likely we've got raised to another function. So if we let y equal different notation again, log of x all to the power of 3, then dy dx, remember we have to bring the 3 down the front, keep the brackets the same and subtract 1 from the power, and multiply by the derivative of what's inside the brackets. The derivative of log x is just 1 on x. And then we could write this a little bit nicer, I guess, all as one fraction. Just like that. Okay. Now, in last question here, we can either... we're going to use the second log law to split this log up into the log of the numerator minus log of the denominator. Because remember that second log law can combine them to be the division, which is what you've got at the moment. So if we let y equal that, then to find the derivative, we just need to differentiate each one separately because of that minus sign in between. So dy dx is going to be the derivative of x plus 1, which is 1 over x plus 1. And then the derivative of x minus 1 is 1 over x minus 1. Okay, and then we could find a common denominator, which is going to be the difference of two squares there. X plus 1 times x minus 1. Which means you'd have an x minus 1 up here, minus an x plus 1 there. Don't forget to put it in brackets, because then you can see that x minus x, you'll have x minus 1 minus x minus 1 when you expand those brackets. I might change the denominator to be the difference of two squares. Then collecting like terms, x minus x is 0, negative 1 minus 1 is negative 2. So you've got negative 2 over x squared minus 1. Okay, now find the equation of the tangent to the curve y equals log x at the point where x equals 2. So remember, the tangent is a straight line. To find the equation of the tangent, we want to use maybe the point gradient formula, which means we need a point. We've got the x coordinate at point. To find the y coordinate, we'll sub it into the original equation. And then we also need the gradient. So to find the gradient, we need to find the first derivative, which is also called the gradient function. So if y equals log x, then the gradient function, dy dx, is equal to 1 on x. We want to find the gradient at x equals 2. So at x equals 2, the gradient of the tangent will be the gradient of the first derivative. So subbing in 2 for the x there, and we get half. And so we've got our gradient now. We've got our x coordinate. Let's find the y coordinate. So the y coordinate is going to be, there's the equation to find the y coordinate, and remember we've got x equals 2. So our y coordinate is just going to be log 2. Alright, we could even write it like this, log 2. Alright, so using our point gradient formula to find the equation of the tangent, so y minus y1 equals m outside of x minus x1. Subbing in to there, we'll get y minus log 2 equals the gradient, which is half. So x minus x1 is 2. There's our x1, there's our y1, and there's our gradient. Alright, now let's do the fraction to put it in general form. So we've got times everything by 2. So 2y minus 2 log 2 equals x minus 2. And in general form, the x coordinate will, the x value will go first, then the y. So we move everything to the right hand side. And we've got plus 2 log 2 minus 2 equals 0. I like to put our equations of straight lines in general form. In general form, remember, the x goes first, then y, then the constant, and the coefficient of x is positive in general form. To see questions, maybe pause the video now and have a go at these questions yourself first, and then come back and see if you've got the correct answer. So, differentiating log of 5x plus 2. So we want to find the derivative of log of 5x plus 2. And that's going to be the derivative of 5x plus 2 over 5x plus 2. Easy marks. And this other HSC question from last year's HSC, differentiate e to the x times log x over x. So we have a function multiplied by another function, and then divided by another function. So we're going to have to use the quotient rule here, but when differentiating the numerator we have to use the product rule. So let's set it all out properly. Our u is going to be the numerator, e to the x log x. Our u dash is going to be the derivative of that, but we're going to have another set of u dash, etc. So let's set the new ones up in blue. So u now is e to the x, u dash is also e to the x, v is log x, and v dash is 1 on x, which makes u dash, so we have to use the product rule. So we've got the blue, all the terms in blue there to use the product rule to differentiate u. So u dash is going to be insides plus outsides. Okay, so there's our u, there's our u dash. Our v is our denominator, which is x, and our v dash is the derivative there. So now to differentiate e to the x log x over x, we need to use our quotient rule. It's a big question, this one. So our quotient rule is insides x times all of that. Ooh, so we've got x e to the x log x times, well, can you see here when we've got e to the x on x times x, the x time over the x is going to cancel, so we're just going to be left with e to the x there. And then the quotient rule is minus the outsides, minus all of that, which is e to the x log x all over the denominator squared. Can we cancel anything? X e to the x log x plus e to the x. No, we can't really cancel anything. Maybe to make it nicer we can take out the common factor of e to the x, and we'll be left with x log x plus 1 minus log x all over x squared. And there's our derivative.